Okay, so now here we are coming back to talking about risk and hazard, the difference between the two. Okay, now remember, risk will increase in places that people are more vulnerable to them. So places, for example, if here in the western United States, they tend to be more prepared for earthquakes than we do here in the eastern United States. So we're in some aspects more risky. It's riskier for an earthquake to occur in the eastern United States because we're not prepared for it, whereas the western United States is more prepared. But their frequency actually outweighs more of the risk than our frequency because we don't have as much. So, however, we do have earthquakes in the eastern United States. Here's an example. Over the past 400 years, there have been more than 30 damaging earthquakes in the eastern United States, ranging from a 6 near Boston in 1755 to a 7.3 in Charleston, South Carolina in 1886. So we've had some large ones, some small ones. They've caused a little bit of damage here and there. Now I'm going to focus on the one that happened in Charleston for a little bit because that's pretty close to home for us here in southern southeastern North Carolina. Okay, so this is the modified Mercalli scale graph of how far where the effects were felt from that Charleston earthquake. Now remember, a 10 here is pretty much is pretty much a lot of destruction. I can't remember, and whereas a 5 or a 7 where we're at here. Okay, let's go back to what a 7 would be on our scale here. Oh, I went too far. So a 7 here would be everyone runs outdoors, damaged, negligible in buildings, good design and structures, slight to moderate, well-built, ordinary structures. Poorly built structures would be damaged, some chimneys broken. So we wouldn't have a lot, but we would have enough where we could have damage to our foundations and things like that. If the earthquake in Charleston happened again, right? That same size earthquake did. Whereas in Charleston themselves, they had quite a bit of damage. There was a intensity of a 10. They had about 60 to 114 people lose their life during this earthquake. A lot of liquefaction. That's basically when the sand shakes so much that the buildings on top of it start sinking into the sand, kind of like quicksand, and we'll talk about that a little later. But if we base it off of U.S. dollars in 2014, it would be an estimated of $125 to $240 million in damage. So it was pretty significant. So here's some pictures of the actual earthquake itself, and the after impacts of the earthquake. You see some of the notice the brick buildings don't actually fare as well as some of the wooden buildings, but there's still the damage that you can see throughout those regions. Well, what are some of the hazards related to earthquakes? Now, remember, a hazard is just a potential damage or potential loss of life or anything like that. Okay, so these are the main hazards that can occur during an earthquake. You have the actual ground shaking itself, so the shaking of the ground, or the displacement, the ground rupture or displacement of the ground itself can cause damage, or liquefaction. Those are all what we call primary hazards, which means they are caused because of the earthquake and the shaking from that earthquake. Now, there are other things that can be triggered because of the earthquake as well. For example, a fire can be triggered because of the earthquake, causing gas lines to burst or something like that, therefore break and cause out and have fires. That happens a lot in when we had some of the Japan earthquakes, the San Francisco earthquake, and some of these other ones. They trigger fires to break out throughout the cities. Or it could trigger a landslide, and because that land's unstable, the shaking will cause the landslide to occur, and therefore cause the mass wasting is the scientific term for landslides. And then, or it could be caused by tsunamis. And a tsunami, this is not a real picture, but I wanted to show you this. It's basically this large pressure wave that comes into the land and envelops the land. And we'll talk more about tsunamis when we get to our coastal processes section. We're not going to be talking about. They talked about it in the book a little bit in there, but we're not going to go in a lot of detail in class. But we'll go into it a little bit in just a minute. Okay, so let's start going through each of these. First of all, the ground shaking. It's just that vertical P waves and S waves causing the ground to go back and forth, up and down, back and forth. And this stuff is not as much motion. Remember that the P waves and S waves are lower intensity than the surface waves where it goes back and forth through this way. So it's during the earthquake, the ground could shake and cause damage to electrical lines, roads, buildings, a lot of different things. Okay. So here's some examples of what ground shaking could do. This is the 1989 earthquake, the Loma Prieta earthquake, or the World Series earthquake, if you want to call it, where this building here, the bottom floor was just garages. We call that a soft story. So it doesn't have a very good structure at the top. So here's all this weight on the top of this soft story down below, and so it's not built very well or designed very well. So therefore, the bottom structures failed, and the top structures collapsed down on top of them, and that's why some of the damage occurred in this area. Also, the resonance of waves as they go through certain things will shake more from certain buildings than others, and so this is an example of that in Mexico City, where all the structures just collapsed on top of each other. So this is, I don't know how many floors this is. It's like 6 floors, 1, 2, 3, 4, about 6 floors or so. They just collapsed down on top of each other. An example of this one here in Armenia, but it's just that shaking, which actually some buildings will not stand up to it as much. Brick buildings mostly, wooden buildings tend to actually sway more with the structure. We'll talk more about that in a second. Now, liquefaction is also a primary hazard, and what's happening here is oftentimes when we have saturated sand or materials down below, the pressure from as it shakes is forcing all those materials downward, causing sand blows to come up. So you have pressurized sand going up and doing these little, what we call sand blows or sand volcanoes. Or you can actually cause the material itself to actually sink. Okay, so here's some examples. Here's some of the sand blows that are occurring during the Japan 2011 earthquake. This is in a park that is an old landfill that they put, so there's a lot of water in it. And so as soon as everything started shaking, it pressurized all that sand upwards and formed these little sand blows everywhere. Now this one here is Christchurch, New Zealand, along the Alpine Fault. What happened here is the sand actually going back and forth. It's kind of like when you go to the beach and you go on the sand, you start rocking back and forth, you'll start slowly sinking down. Basically what's happening is the sand is flowing away from you as you're adding pressure to it. And this is what happened to this car. It basically went straight down, just like quicksand. And then after it stopped shaking, it basically got hardened. So now that they had to dig this car out, it's kind of cool here. This is the same example of Mexico City. The buildings sank. You can see that this is where the doorknob should be. It went about half the whole floor of the whole building went down because of its weight. And the material didn't go down. This time it went up because the sewer system is mostly air with just water flowing through it. And so what happened is the materials flowed underneath the sewer system, popping up the sewer system, right, out of the ground. So this is all examples of what we call liquefaction. Another thing that could happen is what we call mass wasting. It could trigger the landslide. This happened back up in Alaska when you had a 9.2 earthquake. This whole area, when it shook, basically sloughed off to the side, off into the ocean, causing a whole subdivision to actually be destroyed. This is the Turnagain Heights area. Here's the school that got ripped right in half. You can see the buildings throughout here that got destroyed. This happened up in Alaska back in 1962. Other ones can have your primary hazard of rupture. Okay, so you can have the roads actually get cut in half. This is actually a building that got cut in half. This is the garage, and this side went up, this side went down. It's a normal fault. You can see this over here. This is a campground. I take students to. This is near my house, by the way, up near Yellowstone. And this side went down, this side went up. Normal fault again, forming an earthquake. Forming a waterfall as the river went over that edge. And then this one, the whole valley sank, causing the lake to shift over, flooding homes that are now completely underwater. Okay, that's all happened up there near Yellowstone National Park. Fires, a secondary effect, breaking gas lines or any fires at all will spread to the systems. Often you don't, because of the damage, fire trucks, emergency vehicles, and stuff like that can't get around, and therefore the fire spread throughout the region. Okay, so that's a big impact there. Tsunamis, also huge impact. These are caused when there's any kind of displacement in the ocean. So for example, if you have two plates right here and one's going down, as it goes down, it actually catches and pulls that down with it until it breaks. The elastic rebound theory, right? And it breaks it back, pushing it back up. When it pushes it back up, it also pushes all the water up. And therefore, you have this big wave that comes in, and it gets bigger as it comes closer and closer to the shore, because there's it's deeper here and shallower here. So all that water gets pushed on the shore. First, it gets withdrawn, and then it gets pushed right back on the shore, flooding the areas. Okay, so this is a normal storm wave, and it will, even in a hurricane, it will only go up a certain distance when the tide goes up a little bit. Tsunamis are kind of like tides as well. That's why sometimes people call them tidal waves. They look like tides coming in, but they're not. Okay, they're actually just these big pressure waves that come in to the area. And we'll talk more about tsunamis later. But one of the biggest tsunamis that we had is one during the Sumatra earthquake back in 2010. 2010, if I remember right. Okay, it's 2011. Can't remember. 2010, it was December of 2010, if I remember right. And that tsunami wave went all the way across the ocean, hit India, Sri Lanka, Indonesia, caused over, what was it, about 30,000 people to lose their lives. It was a huge wave. This tsunami had, its height was about 15 meters, so this is just an example of a human and going through there. I'll show you some video of this guy later when we talk about coastal processes. Okay, so I'm going to skip this one and we'll talk about it more later. Okay, but here's some of the effects of the Japan earthquake and tsunami, completely destroying this home here. Like I said, we'll talk more about it later. Now, when you predict an earthquake, there's really no way to predict an earthquake. There's no long, short-term prediction, because you don't know when that stress is built up enough where it's going to fracture and move. And so, right now, we have no way to do a short-term prediction. Okay? The best we can do is like 30 seconds ahead of time. The reason that we can do it 30 seconds ahead of time is the difference between the P wave and the S wave. Okay, so if the P wave and the S wave, arrives, we know an earthquake's coming. Well, we might have 30 seconds before the S wave comes, or less, depending on how close to the earthquake you are. And so there are systems in place. For example, in Japan, they had this, where the P wave arrived, and it was a big enough P wave that it triggered their notification system, where it sent out texts to all the populace around Japan, and what they had is about a 30-second, 40-second warning that there's a big earthquake coming. Well, 30 seconds or 40 seconds, you could do a lot in that time frame. It would be enough time to register, oh no, I'm in trouble, and try to maybe get underneath my desk or something like that. Whereas if I had no notice at all, I just have things start falling down on top of me, right? That 30 seconds can save lives. And so it's something that they have in place in some places around the world. The U.S. don't have this in place yet, and I just don't understand why. They should have this in place, especially some of these larger cities where earthquakes are common, like Los Angeles or San Francisco. But they need to put them in place. And what they do is they also put them in place to shut down power, to shut down gas lines, to shut down subway systems, stuff like that, to be able to mitigate or lessen the impacts of the damage that occurred there. Now, the better way for us to actually predict an earthquake is what we call long-range forecasts, where how long has it been since we've had our last earthquake, and how big was it in the past. So by doing that, we can predict them and say we have maybe a 20% chance that it's going to happen in the next 50 years or something like that. So it's basically a statistical analysis at that point to try to figure out when the next earthquake is. Okay? So these long-term predictions are based off of looking at geological features, dating them, seeing how often it occurs in that area, and then making estimates based off of that. Okay? Or you can do early, like the buoy systems like they had in the Indian Ocean, or Japan for when the tsunami hits. But those are the only kind of warning systems we have.